This presentation highlights the integration of various AI techniques together with PSE methods and tools for intelligent process synthesis, design, analysis, and innovation with the objective to achieve sustainable development goals. In particular, the concept of ease-files with associated hypergraphs are integrated at different steps of the workflow for synthesis, design, and innovation. This work is done in collaboration with Columbia University. The presentation highlights 1. Use of domain, a priori, knowledge coupled with established PSE methods and tools. 2. Use of AI techniques, in terms of knowledge representation, symbolic AI, and generative AI. 3. Use of hybrid modeling techniques, that is, a collection of models of various complexity, such as simple, surrogates, rigorous, and predictive, as well as databases filled with data from ML-based models. 4. Development of a smart software architecture for flexible plug-and-play of diverse software tools, including the workflow and data flow for problem solution. The ProCAFD software allows several entry points, for example, new process where flowsheet is not known in step 0, flowsheet is known but design is not known in step 5, flowsheet and design are known but not analysis in step 8, flowsheet, design, analysis are known but not integration or optimization in step 10, and finally, all from previous are known but feasibility of intensification is not known in step 12. The well-known HDA process for hydrodilkylation of toluene to benzene is used as an example for this demonstration. Other case studies are available. The first step is to define the problem. Data needed are the following. 1. Chemicals present in the system, top left. 2. Input streams, flow rates, temperature, pressure, top right, input arrows, just give approximate values. 3. Output streams, desired flow rates, temperatures, pressures, top right, output arrows, just give approximate values. Based on the input and output streams, the system will point out if reaction data is necessary. If yes, the system will ask for reaction data. In the HDA process, hydrogen and toluene react to form benzene and methane. In a side reaction, some benzene is converted to biphenyl, therefore, the reaction condition needs to be selected carefully to obtain the desired reaction selectivity. See slide 54 for more details on the reaction data page. This option is under development. In this step, using data retrieved from databases, a priori knowledge as well as generated data, analysis of the mixtures are performed, a list of all binary mixtures in the chemical system is generated, a brief mixture analysis description can be viewed at the top left corner, analysis of each binary mixture in terms of formation of azeotropes, available driving forces for separation and formation of eutectate points can be viewed at middle left, a binary ratio matrix where the rows are binary mixtures and columns are property ratios is generated using pure component data retrieved from databases at top right corner. A table of feasible separation techniques where the rows are binary mixtures and columns are feasible separation techniques are generated using symbolic AI at middle left. Click on View for Binary Ratio Matrix to get an overview of the theory and method for calculation of the elements of the matrix. Click on View for Feasible Separation Techniques to get an overview of the list of the separation techniques available in the database together with the list of properties that influence the associated separation technique. Based on the data generated in Step 2, the corresponding process atoms are selected from a database of process atoms and a knowledge representation system. The in-house database of process atoms are continuously extended to allow new process representations. For the HDA process, 2 input atoms, 4 output atoms, 1 reactor atom, and 175 separation atoms have been retrieved. Question: how many process flow sheets consisting of the 6 input, output atoms, 1 reactor atoms, and at least 3 separation atoms be generated? See the next slides for the answer. In this step, instructions for the superstructure generation and types of operations, process atoms, are shown. For the HDA process example, Should the flowsheets to be generated include all types of separation process atoms or only operations involving the vapor-liquid separations? See top left. User may provide their own known flowsheets. See middle left. If binary pairs are identified to form azeotropes, then special solvent-based process groups, combination of process atoms, see top right. This option links to the solvent selection toolbox, ProCAFD. Note that in this HDA example, no flowsheets are specified by the user and no binary mixtures are found to form azeotropes. We select the option for distillation and flash operations, that is, vapor-liquid separations. In slide 55, we show the total number of flowsheets generated if no filter is used. Based on the information from step 3a, first a superstructure is generated, which can be viewed by clicking on the highlighted box 1, flowsheet hypergraph, and box 2, superstructure hypergraph, as well as EASE files of the superstructure. Based on the superstructure, all feasible flowsheets are generated and represented by their EASE files, see top left. Clicking on View for the corresponding EASE files, the flowsheet diagram can be viewed. Note that to draw the flowsheet, the EASE file is used as input. Clicking on box 3, the simplified flowsheet for mass balance is shown. Clicking on box 4, the hypergraph of level 0 can be viewed, only connections of operations and streams and trace of compounds in the system. Clicking on box 5, the hypergraph of level 1 can be viewed, level 0 details plus operation details. Note that the EASE files at this point are based only on mass balance. Note that a knowledge representation method, a method of generative AI, and the passing of data for graphs and vice versa are employed here. See also slide 55 for the total number of feasible flowsheets that can be generated within a few seconds of computer time. Here the generated superstructure for the HDA process is shown. Click on box 1 on slide 6. Note that the system knows that after the reactor, there are a minimum of 3 separation steps and all the alternative feasible separation techniques are shown in the superstructure. Redundant process atoms are not used. Note that the superstructure is based on process atoms, that is, nodes. Note that the recycle streams are not shown here. They are identified in the hypergraphs. See the next slides. The hypergraph of the superstructure and the corresponding EASE files of the superstructure is shown. The EASE files of the feasible flowsheets listed on slide 6 are generated from this superstructure. Note that the hypergraph is based on process atoms. The EASE files of the superstructure is given at the top. Simple process flowsheet drawn from the EASE files of level 0, which is suitable for mass balance only. The flowsheet representation in the form of hypergraph level 0 is shown for the top listed flowsheet alternative from slide 6. The corresponding EASE files is seen at the top. The hypergraph of level 1 for the top listed flowsheet from slide 6 is shown. Note that the nodes are the streams and the connections are the operations. The dashed lines indicate recycles. Input and output process atoms are the start and end points of the process. We have added a color coding scheme. See the text on the right. For the flowsheets listed in slide 6, qualitatively correct surrogates have been developed to predict the energy index, the carbon footprint, etc. This can be done for each flowsheet based on the availability of parameters of the process atoms in our database. Ordering the predicted values, the most promising flowsheets can be identified from the predicted data. Flowsheets 2 and 4 appear to be much better than the others. However, in order to compare with known values, flowsheet alternative 1 is selected for the next steps. Note that these surrogates are constantly being improved and updated in terms of new process atoms. This step involves the transition from the synthesized flowsheet to the design of the operations in the flowsheet. In order to perform mass balance, simple models, surrogates of the rigorous models, are used. Each operation model requires a set of model parameters. These are included in the knowledge representation at level 2 as input data. Using the input data, process simulation is performed with simple models. These results are added to the level 2 as output data. Next, keeping the mass balances fixed, temperatures and pressures are assigned to each stream. Next, energy balance is performed. These results are also added to the hypergraph of level 2, which can be now viewed by clicking on the highlighted box. The concept of reverse design method is used in this step, and an overview of the method can be viewed by clicking on Concept View. Hypergraph for the selected flowsheet from slide 11, moving the cursor to any node or connection, the corresponding saved data can be viewed. Hypergraph for the selected flowsheet from slide 11, moving the cursor to any node or connection, the corresponding saved data can be viewed. In step 6, after the mass and energy balances are completed, the system uses reverse design method to determine the rigorous model parameters for each operation in the processes. Note that since each files is only representing mass balance, the hypergraph in level 3 is also adding new operations that includes mass and energy balances, for examples, pumps, compressors, heat exchangers, etc. Note that the input files to perform rigorous process simulations for selected process simulators are created by ProCAFD, and the process simulation run is activated by clicking on Generate. After the simulation run is completed, the hypergraph at level 3 can be viewed by clicking on the highlighted View box 2. Note that the current interface is active for the Aviva Pro 2 simulation system. Other commercial simulators can be added on request. After transfer to Aviva Pro 2 simulation system, the process flowsheet is now shown within the simulator. Note that additional unit operations have been added, for example, heat exchangers, pumps, compressors, etc. Clicking on View, the user can view the simplified hypergraph of the flowsheet with the new operations added. By selecting hypergraph level 3A, the added unit operations are seen. At the top, the is files that now includes both mass and energy balance is shown. In this step, the rigorous process simulation report is transferred from the simulator, Aviva Pro 2 simulation system, to ProCAFD. For further analysis, the import or transfer of the process simulation report is done by clicking on the Import option. The detailed hypergraph level 3B will be seen. See next slide. Hypergraph level 3B, as in hypergraph level 2, both input as well as output parameters can be seen by taking the cursor to the corresponding node and connection. Note that the information stored at this level is used to create the input files for rigorous process simulation. The variables are the same, only the data organization is different. Note also that using steps 6 and 7, the input files for rigorous simulation of any user-specified flowsheets can be created. Also, using the hypergraphs of levels 3A and 3B, alternative flowsheets can be generated. In this slide, the stream data is shown. Hypergraph level 3B, in this slide the operation data are shown by taking the cursor to the corresponding edge. This slide highlights the connection to LCC, lifecycle cost calculation, using rigorous simulation data from slide 16. In this slide the interface for LCC is shown. This slide highlights the connection to LCC, lifecycle cost calculation. On return from LCC, the purchase and utility costs are transferred. Clicking on View HG Level 4A, the cost data can be viewed in the hypergraph. See next slide. The cost for each equipment can be seen by moving the cursor. Note that other costs are being added. This is hypergraph at level 4A. Next, the environmental impacts are calculated using rigorous simulation data from slide 16. Clicking on View HG Level 4B, the corresponding hypergraph with the corresponding data are shown. See next slide. The calculated impacts for the input streams and the output streams are shown. Note that the calculated impacts are based on the WAR algorithm. This is being replaced by the LCA method, Recipe 2016, for all the environmental impacts. This is hypergraph level 4B. The footprints are calculated using rigorous simulation data from slide 16. Clicking on HG level 4C, the corresponding hypergraph can be viewed. The hypergraph for the footprints, moving the cursor, the corresponding footprints can be viewed. This is hypergraph level 4C. The safety analysis is performed using rigorous simulation data from slide 16. Clicking on View HG Level 4D, the corresponding hypergraph with the associated data is shown. The hypergraph at level 4D with the safety data note that this safety analysis will be further augmented with hazardous properties of all identified chemicals, and for any hazardous chemical found, the associated handling information will also be provided. This figure shows the concept of introducing how to point out process hotspots. The red highlighted parts show danger. The blue highlighted parts show options for heat integration. The hypergraph at level 4D, with the safety data, note that this safety analysis will be further augmented with hazardous properties of all identified chemicals, and for any hazardous chemical found, the associated handling information will also be provided. Calculation of sustainability metrics using rigorous simulation data from slide 16. Clicking on View HG Level 4E, the corresponding hypergraph can be viewed. The hypergraph of level 4E is shown here. Note that for any process alternative, all the generated hypergraphs together with their associated data are stored so that they can be viewed and changed according to the user needs. Using all the analysis data, process hotspots, that is, locations where the process may have problems, are located and targets for improvement are defined. These targets are met through process integration. Step 10, process optimization, with or without heat integration, in Step 11. In Step 12, options for intensification are explored and implemented, if feasible. The final process at the end of Step 12 is a more sustainable alternative compared to a base case at the end of Step 7 or user-supplied. In this step, all the input and output stream data related to heat exchangers are passed to this module, which then performs heat integration by the graphical pinch technique. The mathematical programming technique directly linking to the process simulator is also available. See Step 11, slides 38 to 39. Based on the identified hot and cold streams, the pinch diagram is created to find out the minimum additional heating and cooling that are needed, that is, how much fresh utility can be saved. The concept of simultaneous heat integration of process optimization is highlighted here. The setup for the HDA process for heat integration and process optimization in AVEVA Pro 2 simulation system is shown. The external user module with transshipment model, the optimizer and calculator are highlighted in the blue circle. To perform the heat integration and process optimization simultaneously, it is necessary to include the heat integration module as an external module representing the transshipment model and its associated LP solver. The starting point is a converged process simulation, to which is added the optimizer with a calculator, and the external module is added to the calculator. The blue circles indicate sequential heat integration and process optimization. The red circle indicates the simultaneous heat integration and process optimization. Here, the integration problem, represented by the transshipment model, is added to the calculator of the optimizer as an external module with its own LP solver for the transshipment model. It is well known that the simultaneous option gives better optimal solution than the sequential option. The next slide shows the setup in AVEVA Pro 2 simulation system. Setup of the objective function calculator for process optimization is shown here. Setup of simultaneous optimization and heat integration through the PSE for Speed user module within the AVEVA Pro 2 simulation system is shown here. Results of the optimization and heat integration from the AVEVA Pro 2 simulation system is shown here. Verification of the added design changes to the process flowsheet is highlighted here. For Step 12, that is process intensification, the starting point is a process flowsheet with its design and corresponding simulation. The results are used to evaluate if intensification is feasible, and if yes, the intensified design is generated. Using data from the process simulation report, the answers to the 7 questions are determined for feasibility of reactive distillation, divided wall column, or hybrid distillation. As the answers to questions 2, 4, and 5 are not yes, the HDA process flowsheet cannot be converted to a reactive distillation. Note, we have not checked for feasibility of dividing wall columns or hybrid distillation for this example. To highlight the application of Step 12, we show the 3 steps needed for process intensification. First, check the rules, then configure the RD system. If all the answers to the 7 questions are yes, then transfer the data to the process simulator and finally perform and verify the RD operation. See slides 48 to 52 for more details on the solution steps for the methyl acetate example. The methyl acetate process is shown on this slide. A rigorous process simulation of this process is already available. A process flowsheet from a database of processes can be selected for this step. The database, containing many more processes, is under development. On slides 49 to 52, the feasibility of intensification is demonstrated. Rules to check for feasibility of intensification, as all the answers are yes, intensification is feasible. The reactive distillation design template is used to configure the column for simulation. The design data is made ready for export to a Viva Pro 2 simulation system for simulation. The converged simulation results from a Viva Pro 2 simulation system. This is the end of this example. 2 extra slides are included for additional details on Step 1, Reaction Database, and Step 4, Generation of all feasible flowsheets, are highlighted. The user has the option to insert the reaction information or click on Reaction Synthesis, which connects to our Reaction Synthesis toolbox to provide the needed reaction data, complete reaction with stoichiometric coefficients, reaction temperature and pressure, reaction rate data, conversion or kinetic model, etc. This database is under preparation. Without any filters, a total of 340 flowsheets are generated. Note that to simulate all these flowsheets, the corresponding process operation parameters need to be determined first. For example, the permeability of membranes for membrane-based separations.